All right, so welcome everyone to tonight's event. This is a cooperation between the Cloud Native Budapest Meetup, which is an official CNCF community group, and the Future of Data Meetup, which is organized by Cloudera. A couple of housekeeping items before we get to the presentations. So since this is at least partly an official CNCF meetup, please follow the CNCF code of conduct. Basically, just be nice. I don't think this is usually a problem. As you've heard Zoom, there is a recording in progress, and we also may take pictures. So if you don't want to appear in any public pictures that we may upload to the internet, please come to me and we'll take care of that. There are a couple new channels where you can reach us. We have a new website where we will upload the upcoming events and new information about the meetup. You can also send us an email if you want to speak or want to host a meetup. And we also have a new LinkedIn page. So if you want to get notified about new events, follow us on LinkedIn. And also, if you want to become a speaker, a meetup is a great place to start speaking if you want to get into public speaking. So if you have a story that you want to share in the cloud native space, drop us a line and we can schedule you for an upcoming event. Speaking of upcoming events, we have a new, or the next meetup is scheduled for November the 6th, and we are going to celebrate the CNCF 10th birthday there. Information will be available on the website, on LinkedIn, and on the usual channel. So please enjoy the event, and we have the host would like to share a couple of thoughts before we jump into the presentations.
Hello, hello. Thank you. Hi, everyone. My name is Zita Csaba, and I'm representing Cloudera talent acquisition team. And I wanted to grab this opportunity to bring your attention that we have plenty of open positions in different tech stack, in different seniority level. So if you are maybe considering a change, then feel free to click on the website, maybe reach out to us, register or apply. And with the colleagues of mine that you met during the registration, we will be also here during the networking session so that you can hear about the perks, benefits, unplugged days. So thank you for your attention, and I wish you a lovely rest of the meetup. Thank you.
And let me just take a second to set up the presentation. Okay, so hello and welcome everyone. I'm Soma Koltai from Cloudera, and I work in the data warehousing team, where we are working on an amazing service that lets you deploy Hive, Impala, and Trino warehouses in the cloud. But a bit more in detail. Yeah, so today I will talk about what is CDW, just a bit more detail. I don't want to bore you with the technicalities. Then how and why we ended up choosing Cadence. A bit overview about Cadence, basic features and the most important aspects of the functionality. Also how we bridge the gap between integrating the Cadence and our timelines, and some experiences about the production usage of Cadence. So CDW, as I mentioned, it's a service to deploy Hive and Impala and Trino workloads in a managed Kubernetes cluster. Mainly we support Amazon, Azure, and private cloud OpenShift. So basically, yeah, it's also important to mention this is built around our data lake solution. So maybe you know our main offering is the data lake, and you can attach services like machine learning, data warehousing, and so on and so on. So what we do in practice, basically deploy Kubernetes, magic, and some profit. And in a little bit more details from architectural standpoint, we have our control plane hosted at Cloudera, CloudBreak, provisioning service, user management, a shared Cadence, and our CDW, which was originally just a server, nothing more, nothing less. Then we already assume that we have data lake, and that's not important at this point. And then we deploy the Kubernetes cluster where we have shared service nodes and nodes for the workloads. So architecturally, basically, we have a control plane hosted on our side, and everything else is hosted in the cloud account of the customers, which have some technical difficulties, latencies, communications, and most importantly, we need stability. So if we want to create a cluster, consider creating an AWS cluster, it takes like 40 minutes. After that, we have to install several cluster components like networking, storage components, shared services required for our ecosystem like Zookeeper, monitoring, and this whole process can take up to almost 1 hour, and this takes multiple steps. So if we would fail during this process, then it takes much time of the customer's end, because they would have to retry this whole process again and again. So yeah, this is why timing and long-running task and stability is very important for us. Yeah, and the previous state of the server was basically we had a single server architecture, just one Go binary, and that takes care of everything. It's a monolithic architecture. We have these mentioned entities like the data lake and the workloads like Hive, Impala, Reno. And in the system, we used state-based locking, like it's in deployment, it's running, it's in error state, and so on. And we did basically just gate checking that can we do this kind of operation? Can we upgrade when the warehouse is in an error state? Obviously, no. But we can feel that this isn't the best solution to do locking and multixing of applications. Also, we had another issue that by design we inherited. We had some operations in a synchronous request context, but the long-running part, like checking the result of Helm installs, Helm chart installs, upgrades, were done in a background thread. So we didn't have any facility to basically say that I started this installation and I want to wait for the end result. We had to pull background threads and so on. So yeah, and this also points to the direction that we need something that can handle long-running tasks and can recover from failures. Yeah, so, and another addition to this. So a few years ago, thankfully, we hit scaling and performance issues. We got so many customers that basically they bogged down the service. So we had to think about scalability. Of course, we could scale vertically, but that has limitations like the compute size and the budget, and yeah. And also, we didn't have fault tolerance. If this single service instance restarted during an upgrade operation or an installation, usually we receive some engineering escalations, which is not good for us, not good for the customers. Thankfully, this wasn't a common thing, so they didn't leave us for this. But yeah, we had to address this too. And also that I mentioned several times that we had to deal with long-running tasks and provide fault tolerance during these long time periods. Not to mention that if we want to implement some more complex features like rebuilding or restoring the full environment, which includes the cluster creation and the creation of the workloads for a large environment, it could take almost 1.5 hours. And yeah, to say confidently that we won't fail during this 1.5 hours while we talk with at least three or so internal services, the cloud provider, and several other services, also backend services, we need some fault tolerance into this system. So this gets to us to the requirements that we needed something that is distributed, resilient, provides some high availability, and also improves observability, because we want to know what happens in this even more complex system. So the options that we considered, we could, so yeah, start, we had the server, and we store the state in a Postgres database. It's pretty common. I think everyone did that or something like that. The second real solution would be to implement some kind of message queue, like posting jobs in RabbitMQ topics and firing up some workers to fetch those topics and start. This you can get to this point to a proof of concept really fast. But as soon as you want some more complex features like automatic retries for these task executions, worker health checks, or basically not just firing a result and polling for it, but some kind of sane client-side API to implement waiting for these tasks, that's an even growing scope that we didn't want to do. And also we had to maintain and improve it. So basically at this point, we would have to implement some kind of almost Cadence-like features, and we would have full ownership with all of the time slice of it. And enter Cadence, which solves this issue. It's distributed, fault tolerant, and we don't have to implement it from the ground up. Yeah, so I'd like to talk a bit about the Cadence and the key concepts. So Cadence is a fault-tolerant distributed workflow execution framework that allows the programmer for long-running distributed workflows. But how does it do it? Basically, Cadence has two key concepts: activities and workflows. Activities are can be considered the smallest amount of computation that can be done by Cadence. It can contain any kind of code. Also, since it's basically an execute workflow call with some parameters, you can consider it like a remote procedure call with a nice API over it that provides futures, which is similar than to promises in JavaScript. And also there are the workflows, which logically ties together these activities and mainly contains business logic. So an ideal Cadence workflow implementation contains side effect-free implementation for the workflows, and the side effects will be important 2 slides later. And this approach enforces the separation of business logic and the code that has side effects and that needs retries or long running. Also, this is utilized by the Cadence architecture during retrying activities and retrying workflows. And a bit about the Cadence architecture itself. So it's basically a client-server architecture. Everything on the side is shipped by Cadence. You can find nice Helm charts or basically just a Docker compose. It can be fired up quite easily. And in the background, it's already a distributed architecture. Cadence uses Cadence for its own repeated or long-running administrative task. Of course, it needs some kind of database, MySQL, Postgres, and so on to store the workflow and activity states, Elasticsearch for the history, workflow history, and for observability. It provides a nice front end, so you can inspect the task. Also, it has CLI clients and code clients. The CLI clients are mostly used for debugging purposes, and what's interesting for us is the workflow workers, activity workers. That could be the same thing, same client, and the consumers. And in our architecture, we basically use what formerly was the CDW server. We use that as a Cadence client, and also derived from the same code base, we have workers attached to the same Cadence instance. So at this point, it's already scaled, but we didn't have a specific activity or workflow workers. You can do it in the same process, in the same binary. Yeah, and by this distributed design, it's also perfectly, awesomely suitable to run in Kubernetes. Consider horizontal auto-scaling of the workers, deployment of Cadence. It's just perfect together. And as far as I know, Cadence got accepted as a CNCF project last week or 2 weeks ago. So yeah. Okay, this is a bit of deep dive of the Cadence, but the most important part. So I was talking about workflow retries and activity retries, but what happens in the background? Each time the code makes a call to the Cadence API, like execute this workflow or execute this activity or fetch the result of this activity, Cadence server takes a note of that request. So the workflow and activity input is stored, and also some background and internal facts are stored in the workflow history. When an activity is, the activity is retried mostly when it fails. But when an activity failure happens, and the retry policy enables us retrying the whole, but an activity failure doesn't mean that the whole workflow needs to be retried. That's configurable, but basically just retry the activity until we reach the maximum count. If it's okay, then we move forward. Cadence stores the result too, and moves forward with the workflow. But what happens if we had some kind of workflow failure, like simple workflow, fetch some data from the database and install something, and we failed at the fetching step? No, and we succeeded fetching the data from the database, but we failed at the next step. In this scenario, Cadence reruns the exact same workflow code with the exact same input stored in the database and checks whether the next activity input is the same as in the history. If anything differs from the history and between the new retry run, then you will have a deterministic error on your hands. So this is how Cadence uses workflow and activity history to enforce these deterministic criteria for the workflows. Same input, same results. Without this, the whole concept would fall apart. But thankfully, we have guarantees for that, also some nice test suites. So if you have some workflow history, you can use that in unit tests of the code and for full workflow tests too. Another important thing to mention with activities and activity retries, if an activity succeeded, then during a retry, it won't be run again. So the activities don't have to be idempotent. The whole workflow has to be deterministic. History takes care of enforcing determinism, and it takes care of unnecessary retries. So you can easily write a Helm install or anything that has side effect that changes the infrastructure components. Basically, no limitation what you can do in an activity, because it won't be retried when it succeeded. On the other hand, if you fail during an activity and you need some cleanups, then you have to take care of that. So Cadence isn't that smart that it would provide some automatic cleanup features, but there are solutions like now retriable errors to handle these specific scenarios where you have multiple return points of an activity, but only a subset of those return points would mean a workflow failure. Yeah. So basically, Cadence provides us a stable and robust solution. It's battle tested and used at Uber to drive their whole infrastructure. And I think if it's good for Uber, it's good for most of us. It has a Kubernetes native deployment model, distributed execution, scalability by design, fault tolerance by design. And in our specific use case, this also means that we have high availability, since when we move every business critical, every customer critical workflow to Cadence, at that point, we don't have to care about whether the front-end server crashes or gets restarted reliably time to time, because Cadence guarantees us that the workers, the workflows and the activities will succeed. So it's not real high availability, but pretty close to that, and that's enough for us. And from an architectural and coding aspect, yeah, we have workflows, activities, enforced separation of concern, enforced separation of business logic, and actual code with side effects. And also, as I mentioned, it improves testability by providing these tools to reuse the workflow history to run in tests. And also we had some other things to implement because Cadence also doesn't provide us locking or leasing. As I mentioned before, we needed something in place of this is in running state based locking or leasing. We chose leasing, and I will return to that because when you use the simple locking solutions that we already know, you have to unlock it at some times, but we have to assume that unlocking won't happen. So this is, if you basically add time to leave to a lease, to a lock, you will get a lease. Also, we had to implement context propagators. It's a solution by Cadence to propagate contextual data, how to serialize and unserialize it. Also, we had to integrate logging, like Cadence uses Zap, but we use Logras. Some convenience tools, so we don't have to write this boilerplate code over and over. And most importantly, we have to write workflows and activities. But as I mentioned, the system is complex, so we can't just integrate Cadence and write workflows and activities by the next day, because we want to have Cadence access by the next day. So, and also Cadence, by this design, enforces some things like we can't rely on in-memory caches because we have to move from a single server to a multiprocess architecture. So we had to deal with this technical debt, which wasn't a problem when you have a single server scenario, but as soon as you have a multi-server or multi-service scenario, you have to tackle this. So we needed something that looks like Cadence, behaves like Cadence in the most ways, but easier to get started with. And by this, we could achieve that part of the team can start working on workflows and activities and refactoring the code. And another part of the team can start implementing this, all this we need, leasing, utilities, you name it. Okay, so the key requirements were basically, we need something that we can use for background execution, provides the same API like promises in JavaScript or Future in Cadence. So naturally, we choose to basically take the best parts of the Cadence API and model our internal solution based on that. So we have similar API signature, and in hope that we will, that by using this, resulting code will be reusable in Cadence. There will be only 2 or 3 slides with code, so this is the simplest workflow you can do with Cadence. You have to set up some things like timeouts. These 2 are the mandatory timeouts, heartbeating, weather event cancellation. You attach these options, you pass these options through context, then the magic happens. We start the activity with the passed values, and we receive the provisional response. At this point, this is running in the background. If we call get, that's the blocking call in Cadence. So this is what I was talking about when I was talking about futures or promise. Basically, the very same concept. Okay, so now we have the limited feature set that we have to implement. We need some kind of activity handler registration. We need some way to pass options to the execution, and also related to the code execution, we need this provisional response, input and output serialization, context propagation, and some kind of panic handling. This sounds like a lot, but in practice, this can be implemented in like 600 lines with 1,000 lines of test for 100% coverage, and took us like 2 weeks and some preparation time. So considering to the time frame of a whole integration project, which took more than 1.5 years, investing 2 weeks so we can parallelize the tasks and start simultaneous development of new features, migrating the code, and also integrating Cadence. we have to sacrifice these 2 weeks, but I think it worth the time. And the end result, I showed you how our Cadence workflow looks like, and this was done with our internal tool, which pretty much, I think, looks like Cadence. Yeah, a bit about how so I was talking about activities and activity handlers, but how does it looks like in practice? So activities can be invoked from multiple workflows, and also in a Cadence environment, there's no guarantee that those activities will be run on the same machine, which naturally means that these activity handler implementations must be stateless. Only use the input, but of course you can use some kind of dependency injection or so to compose these activities. But the key takeaway that those have to be stateless, and also you have to count on that the inputs and outputs are serialized. So no more passing channels and callbacks and other high-level stuff. You have to resort to simple serializable objects. So simple example like this, you just include the dependencies, write the handlers. This is reusable. You can use it in our internal implementation and also in Cadence. So at this point, we already had some basic workflows, basic activities. We had our activity handlers, and we had something to run these, but still no Cadence because we needed some things to do first, like solve the issue of this distributed locking. We had to get rid of the in-memory caches. Also, we had to deal with some stateful global components, with dependency injections, and also we had to provide some administrative features for handling these leases, so we can save the day when something gets stuck and deadlocked. Okay, so we implemented this lease API in 2 steps. The first step was to do something which works without Cadence. Very simple API. We can acquire resource operation ID, a time to leave, and a wait period. So we can say that we will wait 5 seconds to get this lease or fail. Or if it's a very important task, we can say that we wait 0 seconds, either give me a lease or fail fast. Also, we included some limitations in it. So only 1 lease per resource. We don't want hierarchy between leases because that would bring us to a very new level of hell. I mentioned the wait period and also lease, one important aspect, it can be extended. So since we don't know whether we will finish in 5 minutes or 15 minutes, we needed facility to extend these leases during the time period of the computation. And the backend was implemented using a simple Postgres database. We checked for solutions like Redlock and so, but everything was far more complex than what we needed, because honestly, this isn't that complex than the solutions out there. Also, it needed to be reliable. And also, sadly, we don't need to handle thousands of leases during a second. So from a performance standpoint, using Postgres is more than enough. And the next step was to tie this together with Cadence. Basically, we created a wrapper that works, that invokes this lease service using Cadence activities and starts a background thread for extending leases, similar like heartbeats in Cadence. This may sound a bit like violating this deterministic criteria, but in practice, only the acquire which can't be retried, everything can be handled as it would be a normal part of a Cadence workflow. Yeah. Okay. Shit, I skipped the slide. So when we got to the point where we had everything together, we had workflows, we had activities, we had utility methods to write and extend Cadence workflows, and basically it got adopted by the whole team, and we moved majority of the workloads to Cadence. We hit unintentionally proof of stability. One of my colleagues was investigating restart issue. He just saw that the service got restarted periodically, and we didn't know why. Then he started to check the memory graphs, which showed some kind of memory leak issue, but then we found that we never hit the OM limit. And what happened? Basically, the SRE uses Carpenter to defragment the nodes, which resulted in these unintended restarts. And as I mentioned at the beginning of the presentation, these server restarts caused us many headaches, and few years and one Cadence integration later, this behavior basically, not just we didn't have any issues and escalations, it also masked the memory leak issue. So I think it's a pretty solid proof that Cadence can deliver what they said, that your tasks and activities will be handled properly, it restarts and all. And one more, yeah. So basically what we learned and what we found during the journey, that transitioning from our internal tooling that was designed based on the Cadence API and interfaces, you can use the exact same code in Cadence. So it actually helped the transition. Also, Cadence, by enforcing these limitations, it can reveal some cracks in the architecture and the implementation, which for us was a good thing. Basically, this means that we can get rid of technical debt while integrating with the new feature. So I think it's a double win. Yeah, so by impacting our architecture and also it improved testability, and at the end of the day, it improved code quality. And by improving code quality, and I mentioned dependency injection. This green line, this get server context call, is a call to our singleton shared service container, which we found that incompatible with Cadence workers. So this line represents how we could get rid of this vintage kind of dependency injection while we moved our workload to activities, async execute activities, and this is the Cadence part. So this is where we actually started integrating with Cadence, and Cadence activities and workloads started replacing our previous solutions. So that was all. Thank you for everyone for listening. Questions?
So sorry, I didn't understand in the beginning, but the workflows and the activities in hierarchy are basically the workflows can call activities, but it's that there can also be a standalone activity as well, or it always lives together with the workflow.
But if you want more complexity, you can start another workflow from an activity. So there can be child workflows and child activities.
So I do think one of the more interesting parts about these tools like Cadence and Temporal, and also Azure Durable Functions is very similar. So maybe people also work with that, is the durability parts. Like, could you explain about that? Like when you can sleep on a year in a workflow without any issues, etc.
I think the most interesting part is basically the architectural concept, like mixing this deterministic criteria and this enforcement of separation of business logic and side effects. And yeah, you can use Cadence to wait for almost a year. So as long as your Cadence service is running, there's virtually no limitation. So you can use it to, for example, implement package tracking with manual steps. Yeah, and it's implemented in a very efficient way. So during that 1 year period, the workflow doesn't actually runs. It's in a sleeping state, and Cadence takes care that, oh, we had a scheduled run for 1 year later, and when the point in time comes, it will wake the workflow, run with the mentioned input parameters from history, and yeah, we can continue 1 year later with the workflow. But we didn't have to use that, so yet.
My question would be, why Cadence and not one of the alternatives? I guess you did some evaluation, and it would be nice to hear.
Yes, the other possible alternative was Temporal, and the decision was quite simple. We already had Cadence managed by SRE, and yeah, the best way and easiest way to run is if someone else manages it for you. But we were considering Temporal since back then the selling point would be that it uses gRPC and also has some more advanced constructs than Cadence. But since that, as far as I know, Cadence also uses gRPC. So there should be no discernible performance penalty if you use Cadence. But as far as I know, these were the two main options. Maybe we could have been think about using Airflow, but Cadence basically suited our requirements so well that the real decision was whether to use Cadence or Temporal.
I think you talked about this in passing, but so if there's an activity with side effects and it fails after it's already done something that affected something else, so it's a side effect, yeah. Is it the activity's responsibility to clean up after itself before returning to the failure code, or is there an interface for handling these cleanups?
Is the responsibility of the it's a shared responsibility. So mainly the responsibility on the caller, because that's where you can define the retry policies, that how many times would we want to retry this, and more importantly, what are the non-retryable errors. So if there are already well-known error types, then you can basically utilize that without any modification to the activity. But if you don't have specific errors or specific error codes for to discern between failure and retryable scenarios, then you have to modify the activity. But basically, the responsibility is on the workflow side.
Okay, so we'll continue with the second presentation from Adrian, who is going to talk about tracing, OpenTelemetry and stuff. So please welcome Adrian.
Hello, everyone. I hope that I'm fine to hear. I will address this comic later. And today I would like to talk about my tracing journey, how I got familiar with OpenTelemetry tracing in an actual control plane environment, and what I learned. Okay, so briefly, I'm working as a software engineer. I worked as a site reliability engineer before, and currently I very much into distributed systems, developing and operating these. Also, I'm quite close contact with observability domain to help me along these challenges. To start our journey, let's have a problem. After trying to circulate what's our problem domain, let's identify 3 main functions that we would like to tackle. Basically, working our way through data. And because our problem domain is quite wide and quite heavy, we would like to use multiple machines across different deployments to utilize our solution. And we would like to be quite controlling on how we approach this. So what we learned in the past 2 decades that we would like to shift our efforts towards declarativeness, because it makes our understanding and way a bit more comfortable, especially with these distributed systems. So let's say that we have a distributed database where we state our declarative configuration, and we have these agents that we implemented how we would like to tackle the world. But of course, if we have this declarative approach, then we need actuators to actually move our logic forward. And some other components will be naturally implemented or incorporated in this architecture. And I think that's a reasonable mental model to start our journey here. So I'm focusing on distributed systems. And this is how I want to have us this example to help us better understand what's going next. And when I mention distributed systems, it has a lot of quirks, like relaxed consistency requirements. It's not true, for example, that we can read our modifications after a successful update write. We have multiple replicas, network latencies, retry mechanisms if we incorporate that, and many other complexities that will hide between network calls, procedure calls, every kind of race that you can imagine and what you can't. So what is tracing? What is a trace? What is a span? Span is a fancy log line, if you want. It has a name, a specific interval when it happened, optionally apparent, and some extra metadata to contextualize it. And basically a trace is just a bunch of spans. Like you have a system response for a given event. In many conventions, this is what should be captured as a trace, a given system response. In most cases, user interactions. And here, particular span is highlighted in what deployment component, and the name of the span here is ClickHouse query. So as seen here in Jaeger, that for a given trace, you can explore the spans and get a mental view on the attributes, on what happened. And for me, what leads my eye is the name of the span. And the question arises that, okay, can I get the same mental picture as an observer with logs? Probably yes. If you are familiar with SSHing into multiple computers or having a good log aggregator system, then probably you are familiar with the approach that you see a bunch of snippets, text snippets on a big bunch of text. It's doable, but what I learned is that it's zero effort to visualize what's going on with tracing. Okay, let's suppose that we would like to continue our journey on investigating or investing in instrumentation, the way you would get traces out of your existing code bases. And it requires work. It's a nice promise to have zero code approaches, automated instrumentation, and it will give you the service calls, HTTP and gRPC service calls between your services. It's currently in the Golang ecosystem is done by eBPF, if you heard about it. Basically, it's a just-in-time interpreted language in the Linux kernel. It will capture your incoming and outgoing packets. It will check if it's a service call. It will, I guess, snapshot the stack call that you are having, and it will try to identify what Golang library it issued it to extract the metadata. So for me, it's a bit magic, and to help my understanding, it's not enough to have the service calls between my services, because I'm a developer and I would like to use it to understand what's going on. So that leads me to the manual instrumentation part, and I'm lazy in that front. So I try to imagine how can I leverage smarter ways to instrument a bigger code base. How I approached it is identifying component boundaries, handlers, data access layer, other internal or public API boundaries. And after having a little better view as a first step, so other than HTTP calls, then the big step after auto instrumentation is seeing the business domain names, the business model that you think in, or at least I hope you do. As an example, I differentiated like 5 or 6 components. But of course, you can think about a more granular way to categorize your business logic. So for me, these are basically chunks on a map. And after you place the library calls, you instrumented your application to send the spans, batch the spans to a given collector. You face the challenge to manually go to places in the code base to give extra metadata, extra help for your developers. And fortunately, it can be done by placing 1 or 2 lines of code stating that this is the name and this is the attributes you would like to use. If you're a bit more creative on that front, you would say that, okay, this is done, but I would like to generate it. At least it's an interesting thought experiment, but playing it through will result in endless spans, and it is not helpful to see every call in your trace information. So our focus should shift on what's the meaningful data and context we would like to live with, seeing on an average problem. And what is maybe not intuitive on this picture is that the context propagation is seamless in this particular ecosystem on the Golan's part, which I think should be mastered, the context propagation, if you would like to be successful in this area. Okay, I'm talking a lot about context and additional data, how it helps. Let's suppose that our agent reload resulted in an error, and I would like to find out what happened. In this case, I just go up, span, click on the attributes, and check what was the parameters that initiated it, or even the actual configuration that resulted in an error. When I mentioned context propagation, it's also a thing inside the process, but in general terms, it should be interpreted between services in or out of band communication. So because I use an API server in the mental picture, I only had that opportunity to signal what's created, modified in a meaningful business transactional way, the entity. So to connect traces, not spans, but traces, transactions in this manner, I needed that way. But to not create a loop or an endless giant trace for the whole execution, you should be smart on how you make the boundary, but you connect together. I was lucky to have a business transaction that I could connect, basically creating something and then querying it, and the first query until the creation could be this joint. Right. So you get the idea. You cut out the tracing ID, and then you insert it into your span creation. Right. Then is it useful? In this picture, you have two services that queries the database. The first one gets an object, while turning for service B will result in a not found. It doesn't make sense, right? After having the first one successfully get the first one without modification, it can be because of replication lag in distributed databases, and catching these types of errors requires this machinery for me. And unfortunately, I can't go back. But what you've seen is the data access layer showed you the error, and you could correlate it through. Another case for me would be turning a lot of times to data access layer, introducing latency. Okay, it's not specifically tracing wannabe error, but identifying this error have been like seconds instead of catching the logs there. And of course, after the preparated examples, the real world is a bit more complicated. So usually I go through traces like these, and I can, when I navigate, I can spot, okay, there's an error. These are the attributes and the functions that, the business functions that gives me the mental picture, not information, but the mental picture. What should I imagine? Right. As a first approach, I was lost on how to name traces, how to make meaning out of my data. And fortunately, OpenTelemetry semantic conventions and some startups gave their own use cases and best practices on this. The official recommendation is to have what I do on what semantics. But what was a bit more useful for me is concentrating on the notion of medium cardinality, stating that, okay, fine, we are aware that we shouldn't log every access URL there, but to have a grasp on like maybe a couple of tens of items is a good start. To do not put everything in attributes, because my personal experience is that searching spans is not that intuitive. So not everything should be in the attribute section. So span names is quite important for me. Okay. To trying to capture the essence of all of it, it's a funny, new, shiny way to get you to the gist of it, ideally, you see your problem context there, your problem space, and more importantly, everything you need to reproduce an event. I don't know how it resonates with you, but my day-to-day work is about reproducing quite fun events. And it sounds basic to have visual clues on query UIs. For me, using up my mental capacity to trying to locate something really makes a difference if it's a 1 or 2 second job to locate something or to open like 3 stuff and correlate stuff together. And sorry, it's not free in terms of somebody have to do the job, establishing the boundary separation, making sense of your domain, your code base. But after putting up the instrumentation, having basic boundaries and having some examples of how to do it, my experience is that your colleagues will be grateful to have a leading example, and they will absolutely love in these complex examples to, okay, just like logging, put it there and it will solve your questions, or at least will help on it. So I wouldn't say it's team effort, but a project in itself. I know I should be a friend of building and operating infrastructures, but I opted out of placing it into production. So my experience only tends to use it in a development environment. So I can't say much about it, but unfortunately, it has infrastructural cost as well as logging, but we are not talking about it. What your logging costs in engineering error, in SRE error. So to stretch the possibilities you have here, so you instrumented multiple processes, you instructed them to send it to a central collector or multiple collectors that are aggregated, and then you have the ability to put metadata there, for example, what Kubernetes pods or environment it run in, filter batching, the obvious, and of course, other external mechanisms for other metadata. On query side, you have a few options, a few good databases, but you are quite low on choices how you query it. The de facto way is Jaeger, where you have the operations and a basic opportunity on filtering on attributes, but that's it. You have no options to join traces or correlate it with other signals like metrics or logs. You can omit logs inside spans, but it is not the same as having the logs correlated to spans or traces. Also, I haven't found a good advice, library, convention, a blog post, how to have a common ground with logging. And it's quite frustrating for me. I think a good convention can be made in-housely to continue this journey, but that's a harder engineering decision to make. And as I haven't tackled production, sampling ratio for me was 1:1, which is a nice to have. What I've read is that dynamic sampling is not a thing yet. So I see uninvestigated efforts there to make it viable on bigger scale. And this side quest of mine taught me that I should be more aware how I write my business model, how I express the ideas that matter in a straightforward way that are observable. So after putting in the effort to express what's important, I think tracing and logging will be more expressive afterwards. Because when you develop distributed systems, most of your code is not about your happy path, but edge case covering, which is important in a way. But I guess it's not your focus when you would like to observe any situation. And I hope that in the open source landscape, more visualizers or ways to correlate signals will appear. I really hope that, for example, joining traces with a trace language, I think it's feasible. I see value in it, but I haven't seen it even in upcoming or newer startups dealings. As an outro, I can imagine that having all these executions, you could, with a data mining knowledge or with a language model knowledge, you should be able to generate documentation out of it. This is just an idea, of course. And I've also seen interesting efforts on using tracing data in unit integration and end-to-end testing, because if you are familiar with temporal logic or any neighboring areas, you can write manageable temporal logic expressions that you would like to persist as invariants in the system. And if those are violated, then you have an anomaly that you would like to investigate on. Thanks for listening to me, and do you have any questions?
Thanks. So you mentioned correlating, or the need for correlating logs, metrics, and I mean traces and metrics. So metrics should be the hard part of it, because it's not that labeled data as a trace would be or a log would be. have you considered, but structured logging has become commonplace, so it's quite easy to parse. Have you considered using some kind of transformation or basically providing a layer to use structured logging and connect it with traces, or for maybe example with Jaeger? Because for example, in our system, we at least include request ID, which can be used to correlate the request across services. We have the structured log lines, but there's some missing piece, but it almost contains every information that a trace does.
Thank you for the excellent question. So my go-to way would be to utilize OpenTelemetry collector to firstly check a time correlation between events, and if you have request IDs, of course, you can also copy the logs into your spans. After tackling the question what span you would like to see your logs within, or if your visualizer system would support multiple queries, then also on the one side, seeing the traces for a given user event and also seeing the logs there would be a way. You mentioned metrics. I haven't done my homework to read more about examples, but they are new ideas how to show you concrete event examples that incorporated in a given metric. So there is a way to see examples for a metric, I think. With that, thank you very much.
Thank you, Adrian, for the great presentation. That's all for tonight. If you want, you can stick around for some networking. But the official event is over. You can grab some more beers. And I think we have to leave the venue by 8 p.m. So we have 40 more minutes. If you want, we can go to a nearby bar and grab a few more beers. But that's the end of the official event. If you follow us on LinkedIn, you will be notified about upcoming events. Again, the next Cloud Native Budapest meetup is on November the 6th. Thank you for being here. By the way, it was really great to see so many new faces. I know a couple of you, but I usually know at least half of the crowd. That's definitely not true tonight. So really great. Thank you.